Hello everybody, in this lecture we will be solving 1993 IMO problem number 3. It is a combo problem, and here is a view of this problem. On an infinite chessboard, a game is played as follows. At the start, n square pieces are arranged on the chessboard in an n by n block of adjoining squares, one piece in each square, and a move in the game is a jump in a horizontal or vertical direction over an adjacent occupied square to an unoccupied square, like in the game of chess. Not like in the game of chess, sorry. Checkers, yeah, like in the game of checkers. The piece which has been jumped over is removed. Find those values of n for which the game can end with only one piece remaining on the board. So if n is equal to 1, can we accomplish? Yes, we already did. There's only one piece on the board and we are done. What happens if n is equal to 2? So we have so 4 pieces on a 2 by 2 block, and how can we start eliminating them? So let me go ahead and get my erasing tool as well. If you guys are ready, let's do it. I will first start with this piece here, and I will jump it over the other guy. So this piece will come here, right? And as a result, it disappeared. And because it jumped over this one also disappeared. Oops, disappear, mister. Okay, in a similar way, I will make this one jump over the other guy. As a result, it ends up in this square. It is no longer here, plus it jumped over this one, so this one also disappeared. We have only 2 pieces left. Finally, I will take this piece and I will jump it over the other guy. So I am here, and this one disappeared because, and then this one we jumped over it. Wow, so I'm able to accomplish it. How about n is equal to 3? 1, 2, 3, 1, 2. So things are starting to get a bit harder, I guess, right? So you might start playing with this, and after a while you would realize that it's not gonna work, right? So we need to start in either one of these 5 pieces. For instance, if you start with this piece, so I take this piece over here. As a result, these 2 pieces disappeared, and then maybe in order to recapture this guy, I can take this guy over here. So now I'm here, and these 2 disappeared. Now I can move this one back into the game. So these 2 disappeared now, and we have 1 piece here. And then, yeah, I can move this guy over, and now it's here. These 2 disappeared. I don't know, so we can move this guy over here. So these 2 disappeared, and then maybe move this one over here. These 2 disappeared, and now I have just this. Now the problem now, we have three checkers on the board, and 3 pieces on the board, but they are on a line. So what do you do from here? You need to make the move from the mid piece. It will eat one of them. So these 2 cancelled, and we have 2 pieces remaining on the board, which are separated by some spaces in the middle. So we didn't. So you can keep playing this game, and then after a while you realize maybe it's not possible to finish the game as such. In that case, we should be smarter. So the way to handle it will be the following. I will create a coloring scheme. So I will create 3 colors, and I will write the colors in the following way. Either you can think of it like a coordinate system. So let's build a coordinate system here. Let's say that hold on, let's make it on the positive axis. So that's yeah, so like that. Oops, there we go. Okay, and then this. So I'll give the color 0 to this guy. And to this cell, I'll give the color 1. To this cell, I'll give the color 2. So what I'm doing here is x, y axis. So if the sum of x plus y is equal to 0, is congruent to 0 mod 3, I'll give the color 0. And if it's congruent to 1 mod 3, I'll give the number 1. If it's congruent to 2 mod 3, I'll give the color 2. So the sum. So therefore, here the sum is 1 plus. So this one is also 1. This guy is 2, this one is back to 0, this guy is 2, this is 0, this is that right? 1. Okay. Now what is surprising is, because we did take in mod 3 and n is divisible by 3, the following happens. So the number of points which are 0 is k0, the number of points k1 is 1, which have a 1 is k1, and the number of points which have a 2 is k2, and initially all three numbers were equal to each other. Now, after each move, so suppose that I take a piece, I make it eat another one. What happens is, and by the way, even those without pieces, we numbered them as well, right? So therefore, this will go on forever. 0, 0, 2, 1, 0, and so on. So 0, 1, 2, 0, 1, 2, 1, 1, 2, 2, 0, and so on. So the whole board should be covered, right? So 0, 2, 1, 0, 2, 1. 1, 0, 2, 1, 0, 2, and so on. 2, 1, 0, 1, 0, 2, 0, 2, 0, and so on. Okay, and let's also finish this guy. 2, 0, 1, 1, 2, 0, 0, 1, 2, 2, 0, 1, and so on. 0, 1, 2. So you get the idea. 1, 2, 0. Okay, so once we start eating the pieces, for instance, let's say that this piece here, it eats this piece. What happens as a result? So these two pieces will disappear and we would have a new piece here. So what will happen is the count of this one will go down by 1, the count of this one will go down by 1, and this one will go up by 1. But what has not changed, so we are looking for an invariant here, I guess, right? The invariant in this thing is the parity. So to begin with, they were all odd or all even, and in each move of eating a piece, jumping over and eating one piece, during this procedure, the parity of ki's do not change. Now, what is the objective of the whole game? To try to just leave one piece remaining on the board. So just leaving one piece on the board means that one of them one of the k0, k1, k2 will be equal to 1, and the other two would be 0. But that's not possible, because in terms of their parities, either all three, for instance, in this particular case, every single one of them was equal to 3. So all three started as odd, and then in the next move they all became even, and then in the next move maybe they all became odd. So they alternate their parity. But no such situation will happen where k0, k1, k2, say, will be like that, right? So because these guys have different parities. So that proves that when n is equal to 3, or n is divisible by 3, I should say, it is not necessarily 3, but when n is equal to 6, things don't change. So 6 squared is equal to 36. In that case, k0, k1, k2 will start as 12, 12, 12. So each one is even. So once, let's say, k1 eats a k2, so a color 1, a piece on color 1 eats a piece on color 2, then both k1 and k2 go down by 1 versus k0 go up by 1. So therefore parity is preserved. So now all of them, so the new count would be, if, as I said, a piece on 1 eats a piece of 2, a piece on 2, it will become 13, 11, 11, right? So you see what's going on. Or for instance here, it became, so for instance it became, so this guy became 2, this one is 2, this one is 4, but the parity didn't change. All three are even, so they alternate, all three even, then all three odd, then all three even, and so on. But no such finish will ever happen. So therefore when n is divisible by 3, there is no solution to this game. Now we are curious what happens if n is not divisible by 3. So far the two were successful. Can we have this run forever? Like for any case, would it work? And the answer is yes. And we can do it by considering the following lemma. I would like to consider the following. And I will write the lemma in terms of a 3 by n grid. So let me create one. So the grid piece that I'm interested is in the following. So let's consider the following 3 by m rectangle PQRS. So it is definitely a 3 well, you obviously see the width is 3, and so this is a 3 by m. PQRS is 3 by m, and all of it is filled with checkers inside. Okay, so there is I mean pieces. It's full with pieces inside, and then I will assume that there's no piece on this guy, but there's a piece on this guy too. Okay, so my claim is the following, my lemma is the following. It is possible when we have a configuration like this to eliminate all occupied pieces, to make all occupied pieces unoccupied, right? So it is possible to eliminate all occupied pieces from the 3 by m rectangle PQRS when we have this special condition, right? When we have a configuration where you have an empty piece here and no piece here, and then there's a piece here, right? We have the configuration on the right side, on the right picture. Okay, so why would that be? Okay, very, very simple. Are you guys ready? Let's just do it. Okay, so no piece here, piece is here. So I'll start with this first column. I'll have this guy eat this guy, so jump over it. Now I move here. These two pieces cancel, they disappeared, and now I have, oops, come on, so I have a piece here. Now what I will do next is I will take this guy, jump it over, come here, these two pieces disappeared, and finally this guy jumps over, comes here, these two pieces disappeared. What has just happened? Well, what has happened is obvious. The 3 by m rectangle shrinked to a 3 by m minus 1. And I can continue playing this algorithm. So in the next move, I will take this guy, jump it over, come here, these two disappear. Then take this guy, jump it over, these two disappear. Then bring this one back inside, and these two disappear. And then boom, another column disappeared. So in a similar fashion, we can make all these columns disappear until the last column. In the last column, thanks to this piece here, which is just available there, I can just jump it over. So this guy will disappear. Come on, just disappear. This guy will disappear, and now we have a piece here. And then this, I will make it jump it over here. These two will disappear as a result, and finally this guy will go back to its original position. Oh my god. So we were able to make all the pieces disappear, and the initial condition is still there. No pieces here and one piece here. Isn't that just beautiful? So therefore, the rest of the problem now will make use of this lemma in an intelligent way. So whenever we have a grid, we will divide it into subdivisions of 3 by m rectangles, right? So as I will do it next, so let me create a random grid here like this. So we have this grid, and let's assume for the moment that all the pieces, this grid is full. So this is, well, in this particular case, I think it's a 1, 2, 3, 4. It's an 8 by 1, 2, 3, 4, 5, 6, 7. Yeah, it's an 8 by 8 grid. Let's see if I can make all these pieces except one disappear from this grid, right? So this is the case where n is equal to 8, right? So all these is filled with pieces. Obviously, these pieces, I mean, we have an infinite chessboard, right? So except that the rest is empty, right? So that's why I didn't even bother. And so you get the idea. So all these places, they are just empty. So, but we can still make a jump over and then land on somewhere there. So which is extremely useful, right? Okay, so how to proceed from here? we will proceed very so carefully. So I will split it into 3 by m minus 1. So 3 by m or 3 by n rectangles. For instance, I will do it like this. Why not do it like this? And then I can do it like that. Why not? I'm just playing with it, right? So as long as I have 3 by n, so that should work. So so why did I do that? So that I can make use of my lemma, right? So let's start with, say, this rectangle here. I have a blank piece here. I have a full piece here. I can do my algorithm, and I can make all these pieces disappear like that, just like that. Apply the lemma. Apply lemma. And the configuration of the lemma is there. We can do it. Next, I have this square here. I have a blank here, and then I have a piece here. I can apply the lemma again. So just do it, and then we can make this whole thing disappear. Apply lemma. Now finally we have this configuration, and I have this one has a piece in it, this one is blank. I can apply the lemma here again. Apply lemma, and the whole thing vanishes. So we started, so check this out, we started with let's say an m by m rectangle square, sorry, an m by m square, in total m square pieces, and we were able to reduce it after applying the lemma intelligently into an m minus 3 by m minus 3 rectangle subret, and now I can keep doing this procedure again and again until it keeps reducing. So for instance, in this particular case, we are able to reduce it to a 5 by 5. So we started with an 8 by 8. In the next step, we were able to reduce it to 5 by 5, and in the following step, we will reduce it into a 2 by 2. But then when it reduces to a 2 by 2, I already proved it early on that it is solvable. The 2 by 2 is a piece of cake to solve. Alternatively, if you have started with a 7 by 7, it would reduce to a 4 by 4 into a 1 by 1, and it means we are done, right? So that's really nice. Well, actually, this game has become so much fun. For the just sake of it, let me just finish this question. So in this case, in the next step, I will just split it like this. Why not? There you go. And then this guy will be like that. And then I will have this guy. I think that should work. Should we give it a try? Why not? So we have a 4 by 3 here. This one is full, this one is empty. I can apply the lemma, I can make this vanish. Then I have this 3 by 1, this one is full, this one is empty. I can make this whole thing vanish. Then I have this 2 by 3, this one is full, this one is empty. I can make this whole thing vanish, and then we will have a 2 by 2 remaining as claimed. So that's a really nice result, and we have just showed that the final conclusion. So conclusion. So the conclusion is that we can accomplish our goal if and only if n is not divisible by 3, right? So the game will end with one piece if and only if n is, or little n, lowercase n, is not divisible by 3, and we have just showed that if n is divisible by 3, no solution. If n is not divisible by 3, I showed the algorithm, a very nice algorithm to do it, and that finishes the proof. So hope to see you guys in our next video.